This is the story of the one. As a maintenance engineer, he hears things differently. To the untrained ear, everything on his shop floor might sound fine, but he can hear gears grinding or a belt slipping. So he steps in to fix the problem at hand before it gets out of hand. And he knows Granger's got the right product he needs to get the job done, which is music to his ears. Call, click Granger.com, or just stop by. Granger, for the ones who get it done.
Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencastr. Zencastr is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencastr has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencastr.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
This is the story of the one. As a maintenance engineer, he hears things differently. To the untrained ear, everything on his shop floor might sound fine, but he can hear gears grinding or a belt slipping. So he steps in to fix the problem at hand before it gets out of hand. And he knows Granger's got the right product he needs to get the job done, which is music to his ears. Call, click Granger.com, or just stop by. Granger, for the ones who get it done.
When it comes to weight loss, no two people are the same. That's why Noom builds personalized plans based on your unique psychology and biology. Take Brittany. After years of unsustainable diets, Noom helped her lose 20 pounds and keep it off.
I was definitely in a yo-yo cycle for years of just losing weight, gaining weight, and it was exhausting.
And Stephanie. She's a former D1 athlete who knew she couldn't outtrain her diet, and she lost 38 pounds.
My relationship to food before Noom was never consistent.
And Evan, he can't stand salads, but he still lost 50 pounds with Noom.
I never really was a salad guy. That's just not who I am. Even through the pickiness, Noom taught me that building better habits builds a healthier lifestyle. I'm not doing this to get to a number. I'm doing this to feel better.
Get your personalized plan today at Noom.com. Real Noom users compensated to provide their story. In 4 weeks, the typical Noom user can expect to lose 1 to 2 pounds per week. Individual results may vary.
Hello, listeners. This is Jonathan Baca.
And I'm Gabriel Hesch, and you're listening to Breaking Math.
This episode is a part in a series about black holes.
You can go back and listen to the episode before this one, but we will recap it before we get into the meat of this episode, so you can listen to this one as a standalone episode.
We hope you enjoy. Previously on Breaking Math.
So in our last episode, we learned quite a bit about the history of black holes. First of all, we learned that the idea of black holes goes all the way back to the 18th century with physicists Pierre-Simon de Laplace and the English cleric John Michel. Back then, they were called dark stars because they hypothesized that light could not escape them. It was pretty fascinating that they thought that an object could be so massive that light itself can't escape it.
Using Einstein's field equations, which describe how curved space makes matter move and how matter curves space, the German astronomer Karl Schwarzschild was able to calculate what became known as the Schwarzschild radius. The Schwarzschild radius describes a sphere. The Schwarzschild radius describes a boundary surrounding a black hole singularity. If you pass this boundary, there is no way of escaping. Light cannot escape this boundary, nothing can. And we talked a lot about escape velocity too.
Right, escape velocity is the velocity that an object needs to be traveling in order to escape a gravitational well. For instance, on Earth, the escape velocity is, what is it? It's pretty fast, isn't it?
It's like 7 miles a second.
Yeah, it's ridiculously fast. Now, in a black hole, the escape velocity is greater than c, the speed of light. And as we know, nothing can go faster than the speed of light. Therefore, nothing can escape a black hole once it has entered the Schwarzschild radius. There were a lot of ideas in the 20th century that were wrong about black holes.
Yeah, before the 1960s, John Wheeler, who was a physicist at Princeton, expressed a belief that black holes are nearly perfect spheres with very little entropy. He said that black holes have no hair, meaning no defining features.
Then in the 1960s, a physicist by the name of Jacob Bekenstein, who was also at Princeton, proved that black holes do, in fact, have very high entropy. Otherwise, they would violate the second law of thermodynamics. He proved this by a thought experiment, imagining a jar of very hot gas where there's very high entropy being thrown into a black hole. And then it was proven that the total entropy of the universe wouldn't decrease if the jar was thrown into a black hole. Therefore, there must be entropy accounted for. And this revolutionized the views of physics.
We also talked a little bit about information theory. One bit of information is a yes or no choice. And we talked about how information theory is related to entropy. The same formula used for entropy in physics is used to describe information. Bekenstein knew that information theory and entropy were related, of course, and he did a thought experiment to that effect to deduce how much mass adding one bit of information to a black hole would add. And mass and the surface area of a black hole are related. And we found out that using a photon with a wavelength equal to the radius of a black hole, the Schwarzschild radius, adding one bit of information would add 1 square Planck length of surface area to the black hole, which is a very tiny amount, but it does not matter the size of the black hole. The same amount of area would be added every time.
That's amazing. So essentially, he showed a model in which one bit of information is sort of like 1 pixel on an HD television, an ultra HD television. But still, it's 1 pixel. I think that's just fascinating.
Yeah, and so the statement that black holes have hair is at an extremely microscopic scale, at the Planck length, wrong, even though at any other scale, basically, it's correct. And we also talked about how information that cannot be retrieved using macroscopic processes, that's to say a process that does not know the exact location of every particle in the system, is called entropy. It's a measure of disorder of a system. So when you mix dye into a glass of water, that it increases the entropy because there's more disorder.
So as you can see, the thought processes and the models for black holes changed a lot in the 20th century. And in this particular episode, we're going to talk about how else it has changed, especially with something called Stephen Hawking's information paradox. That's going to involve quite a bit. One of the things that we're going to talk about before we get into his paradox is a concept of virtual particles.
That's right. So without further ado, here's the episode. Into the Abyss. Black holes are objects that seem exotic to us because they have properties that boggle our comparatively mild-mannered minds. These are objects that light cannot escape from, yet glow with the energy they have captured until they evaporate out all their mass. They thus have temperature, but Einstein's general theory of relativity predicts a paradoxically smooth form. And perhaps most mind-bogglingly of all, it seems at first glance that they have the ability to erase information. So what is black hole thermodynamics? How does it interact with the fabric of space? And what are virtual particles? All this and more on this, part 2 on a series of black holes. Episode 31, Into the Abyss. I'm Jonathan.
And I'm Gabriel.
And you're listening to Breaking Math. Just a quick correction from last episode. When I was talking about the blocks, I said that one of them had 4 bits and the other one had 4.58 bits. I meant 2 versus 4.58 bits because there'd be 4 different ways to arrange 2 sets of blocks in different orders, as long as you're changing the order of each set of blocks.
You know, I'm genuinely curious how many of our listeners actually caught that mistake. Just curious.
We haven't gotten any email from it, but if you want to email us, you could email us at breakingmathpodcast@gmail.com. And of course, you get the Tensor poster on Patreon for a donation of $35 or more. The poster is going to ship probably next week or so. So what are we going to be talking about on this episode?
Follow up to last week. Of course, we already talked about what we did last week. This week, we're going to get more into, I would say the way I heard about this is almost the pinnacle of physics in the last century, and that is Stephen Hawking's information paradox. That's where Stephen Hawking took what Bekenstein had done with entropy of a black hole, and he got into proving that black holes also have temperature, and he also proved that black holes, we'll get into the details here, but essentially he proved that over a long, long time, black holes slowly evaporate, which is crazy. I never would have thought that would have happened.
And by long time, we don't even mean billions of years, which the universe has existed for a few billion. We don't even mean trillions of years. For the largest black holes, they're predicted to evaporate after 10 to 120 years, which is a 1 with 120 zeros after it.
That's just unimaginably long. Unimaginably long. Now, this is an interesting thing, because this is not just some insignificant fact about nature. Black holes evaporating have some drastic consequences, especially for things like basic causality in the universe. Now, there's a show that I was watching a while back. It was on the BBC, and it was called The Information Paradox.
Yeah, I think we might have mentioned that on the last episode.
The BBC documentary on the information paradox is what really got me interested in black holes and in this entire idea. Essentially, this documentary opens up with this idea where the narrator says something to the effect of, what if truly understanding the universe was impossible and science was in fact wasting its time trying to do so? This is one of the consequences of the black hole information paradox.
And of course it's an information paradox because our observations say the opposite, that the universe is very understandable at a macroscopic level.
Yeah.
And so that's what we mean by paradox. We don't mean that they are inherently paradoxical. We just mean that the way that we understand them is paradoxical.
Yeah.
That we used to understand them.
Yeah. And I think real quick, so when we talk about black holes evaporating, this is different from destroying information by burning it. Because obviously when you destroy information, you can certainly scramble it so that you have no idea which particle went where, and it would take you, an impossibly long time to put, all the ashes back together in order to, restore paper. This is actually information, matter, going into a black hole, and then when the black hole evaporates, there's no trace of it again. This represents a problem.
Yeah, because there's not a direct cause and effect, which we'll be talking about. We'll also be talking about virtual particles, and without further ado, here's the episode. Now we're going to be talking about black hole thermodynamics. Thermodynamics is essentially the study of heat. I don't know why it's not called thermology, but there you go.
I like that word, thermology. Yeah, and actually I've also seen it as described as thermodynamics as information destruction. Now, are we talking destruction or information scrambling?
Well, we're going to be talking right now about what would happen if you did destroy information. What would be the consequences of having information being destroyed? Because without getting too much into the next episode, there is the concept of virtual black holes popping in and out of existence all the time, and there's also white holes, things like that, which are the opposite of black holes. But what we're going to be talking about is what would happen if black holes really did destroy information in the universe, even if we don't talk about the virtual ones.
Yeah, and in order to get into those real consequences, like we talk about things like the fact that information is reversible, or at least theoretically reversible.
Yeah, because if you burn a piece of paper, every interaction that is done at the microscopic level, that's key, microscopic, not macroscopic level, is a direct cause and effect. Like the plasma that is generated in the form of fire comes from the excitation of electrons and the emission of heat, things like that. I don't know very much about burning, so part of that might be a little wrong, but there you go.
Yeah. And again, everything still exists, even though it's just big time messy. It still exists. You still have the ashes, the carbon, the atoms are still real. And it's not even a relativistic thing. You haven't transferred the matter into energy, which can happen, but so it still exists.
And at the event horizon of a black hole, which is, you remember, you cannot get information back from, if you think about throwing a book at a black hole, there's nothing once a book passes the event horizon that could retrieve the book. You can't, even if you tie it to a string, you'll probably get pulled in too. So that's why it seems like it destroys information. You could throw, you have a radio station, you beam energy at it, it's destroyed. You throw a brain that remembers things, it's destroyed.
Yeah.
Seemingly.
So and again, now this is just talking about just when you throw something into a black hole. Later, we're going to talk about the eventual consequence of when the black hole no longer exists, which is another information paradox, as it were. But what you're mentioning right now certainly is relevant.
Yeah, absolutely. And so destroying information means generating entropy. And why is this? It's a little bit involved, and we're going to go into that. And before we do that, we're going to remind you that entropy is information that can't be retrieved using a macroscopic process. So if you basically come across a book that's burned, you can't know how to like put it back together, because remember, you have things like Heisenberg's uncertainty principle, which states that you can't know enough to put it back together, basically.
Yeah, and also one of the things that we've talked about before are states, where if you know the order of something, like let's just say you've got blocks that are numbered, or another example is if you've got timestamps on something when they were produced, that information exists. But there are tons of examples in this world where an event happens an order of events happen, and there is no such timestamp, and it becomes impossible to know what order things happened, just because that information is not available.
Let's say you're destroying information. Why does that generate entropy? We're going to answer the opposite of that first. Why does having information mean lowering entropy? And remember, what lowering entropy means is making something ordered. And that can be done as long as you increase entropy somewhere else. An example of that is learning, which you're doing right now, hopefully. When you learn something, you're putting order into your brain. But in doing so, you're burning a lot of stuff in your body. The body is basically a very slow burning reaction. It's oxidization.
And I think it's very consistent with the law of thermodynamics, where the amount of energy that it takes to learn is greater than, or the amount of disorder in your brain metabolizing your food and in your radio or your iPods or your podcast players playing this, that amount of energy is greater than the amount of energy stored, or,
I will say it's greater than or equal to.
Okay, yeah. Greater than or equal to
but probably greater than.
Yeah, the learning that's happening. So although, learning is certainly ordering information in your brain, there's greater than or equal to disorder happening elsewhere.
Yeah, and an example of this is called Szilard's engine. And what Szilard's engine is imagine you have a tube with a divider in the middle of it and two pistons on either end. A piston is kind of like a disc on a pole, kind of like if you took an umbrella and opened it too much. So it seals off each side of the cylinder. Now in this setup, we have exactly one gas molecule. The gas molecule is either on the very left or the very right-hand side of the divider, and there's nothing else in between.
Wow, so yeah, there's no air. So there wouldn't be air pressure, right, when the pistons go in?
There wouldn't be air pressure, but the molecule itself would would bounce around, creating a little pressure of its own. And that's the thing, is that if we know which side the particles, let's say the particle's on the left-hand side, what we could do is we could move the right-hand piston close to the divider and then open the divider up, and then the piston would be pushed back, creating useful work. Now, how did we know this? That's not important, but the fact that we did know this means that we created work out of something that you're not supposed to be able to create work from, which is a microscopic process. So that means that we're lowering entropy.
So in the example of Szilard's engine, you create useful work, you lower entropy, and create usable work.
And because it did that, it expended a little bit of its energy. And remember, temperature is a measure of how much energy is in like a gas or something like that. It's a measure of like vibrational energy. It's a property of a macroscopic system. And we're kind of treating a one particle system as a macroscopic system in this instance because the processes we have are macroscopic. But the temperature of the cylinder is lowered. So we're lowering temperature by knowing something. And we possessed exactly one bit of information, left or right. So one bit of information lowers temperature.
So we know that entropy and information are very similar. So why does destroying information not mean reducing entropy?
And the reason why is, of course, because entropy is not usable information in a macroscopic way. It's like if you translated English to, I don't know, Martian. like you wouldn't be able to get that information back, but it would still exist. So even though it's a hidden information, it still exists. So in a way, because when you're destroying information, you're also taking away usable information, it looks the same to the universe.
Yeah. I can see why this might be confusing for the listeners, because earlier we had said that information is proportional to entropy. The more entropy in a system, the more information. However, that includes hidden information as well.
Yeah, structured information, it does not really contain entropy, and it's kind of a rough model treating information exactly as entropy, because they are slightly different, but they're close enough when you're talking about a macroscopic process, especially when you mean that this is not usable information.
So you say usable. This basically, if I'm not mistaken, correct me if I'm wrong, we're talking about meaningful information. So yes, when you have disorder, there is more information, but meaningful information is, like when you get a word that's in our dictionary, it's a fixed word. But if you add a bunch of more letters to it, there's more information, but it's not meaningful, right?
Yeah, and really what it means in the physical sense, too, it has to do with the second law of thermodynamics. A quick recap of that. The second law means that you can't extract work from a system unless there's a heat difference. There's a lot of energy in the air around you, but if you had a heat engine, you would have to either have an ice cube or a lighter to make the heat engine generate work. So entropy is that cannot be extracted as work. So the crux of this is, if black holes really could destroy information, the universe would get very hot very quickly. It would heat up to a ridiculous temperature in a very short amount of time.
What's interesting is that for so long, Stephen Hawking still held that his information paradox was true. And I'm wondering if the way you're thinking about it is sort of the way Leonard Susskind was thinking about it in some sense. Leonard Susskind had an intuition that the information paradox was wrong, but he couldn't quite formulate why it was, at least for a period of about 30 years or so.
And one of the reasons why is because we understand that black holes exist, but the fact that they have entropy means that there are processes that are going on because there's a right above the event horizon of the black hole, right outside it. We'll go into this next episode a little more, but a lot of stuff is going on right outside of a black hole. And it's my view that this is what happens to the information, that the edge of a black hole is the only thing that exists, and inside of it is something that would be useless to talk about because it doesn't exist. But we'll talk about that more in the next episode.
Before we get more into Stephen Hawking's information paradox, we need to first talk about something called virtual particles.
Which aren't even real particles.
Gosh. So yes, virtual particles are a thing. They're not real, but they are a thing. This is one of the stranger things that I've read about in the last 10 years, and I've really struggled to understand them. I think it wasn't until I was listening to a podcast. I'll go ahead and plug it here. I was listening to a podcast called Ask Science Mike, which is a great podcast, actually, and he actually explained virtual particles, and I think it was fantastic. He explained them essentially by saying that there are fields everywhere in our universe, and virtual particles exist from perturbations in the fields, which is interesting. I haven't thought of it from that aspect. What would you say?
Well, I think we got to talk about what fields mean first, what virtual particles are, and how they're discovered.
Yeah, how many virtual particles are there? You know what I mean? I know there's quite a few subatomic particles. I mean, there's boson, there's W bosons and Z bosons, and the force mitigators and gauge bosons. I mean, I've forgotten what each of those are. It's been a while, but when I think of virtual particles, how they're measurable, and so how many are there? And I guess we also should discuss, why are they called virtual particles if they're not even real?
Well, they were invented by Feynman, and I say invented because virtual particles, because they don't exist until we measure them really, they have to be measured with an increase of energy. Now, let's talk about what a quantum field is, what a field is in physics. Imagine the surface of a very still pond of water, and let's say you throw something in it. It ripples outward. That is kind of that is a wave. And matter exists in waves, but kind of a weird wave that stays around, and where the frequency of the wave is actually the momentum of that particle.
Did you know, I recently read about a physicist, de Broglie, I believe is his name, the French guy, and I think he actually said that if photons can be both waves and particles, then he also said that means that matter or particles can also be waves. Is that related to virtual particles?
That is a little bit related to virtual particles, and how we're going to talk about how it's related, we have to talk about, again, Fourier sequences, which I think we did on an episode called Frequency.
Yeah. So real quick here, just to underscore the point that I just said about de Broglie, that would mean that everything, quarks or neutrons and protons also have a wave property, just like electrons have a wave and a particle property. It's strange.
Yeah, and matter is made out of waves, and we're going to play a sound really quick. That sound is called a triangle wave. Now, a triangle wave can be actually made out of sine waves, which are the purest wave in a sense, which sound like this.
Of course, for our listeners who may be 8th grade and younger, when you think about a sine wave, it's just a very simple oscillation. Like if you're riding your bicycle, it's the pattern that your foot does, the up and down and up and down. That's a sine wave.
Yeah, and the left to right is also a sine wave, but it's in a different axis. And so the volume we could measure that as the volume at any point. For a triangle wave, the volume would go up steadily, then down steadily, then up steadily, then down steadily. And for a sine wave, it would go up slowly, up quickly, slow out as it got to the top, then go down slowly, speed up, and then it would go do that over and over again, like a bicycle. And we could measure it like that, or we can measure the frequency. Now, the frequency of a sine wave is something very simple. It's one number. But what's the frequency of a triangle wave? We could answer this by building a triangle wave out of sine waves. And that sounds like this. You could actually play around with something like this on our website, breakingmathpodcast.com, and go to the Fourier sequence app.
That's right. There's a Fourier sequence app that actually shows how do you describe it? Essentially, you start off with a very, very basic sine wave, almost like, riding a bicycle and pedaling, but then you sort of add sine waves on top of sine waves. It would be like if you added a smaller pedal that spirals around on top of the other pedal, I suppose. I don't know if that's a good example.
Oh, that's a great example, yeah. And then a smaller one and a smaller one and a smaller one.
Things just get crazy.
And the radius of the first pedal would be, let's say, 1 foot. That's a very big pedal, but still. The second pedal would be half a foot. The third one would be a third of a foot, and so on. If you look at the very smallest pedal on something for a triangle wave, it would go up steadily and then sharply go down and then sharply go up.
Yeah, man, I love thinking about sine waves. And then you can talk about things like constructive and destructive interference and how you can change the shape of them and modulate them. It's quite amazing.
And when we're talking about volume, that's a one-dimensional thing with it's technically kind of two-dimensional, but it's one-dimensional at its base because it only goes up and down as time goes on. Whereas matter exists as four-dimensional waves, X, Y, Z, and T, which is forward, backward, left, right, up and down, and past and future. So matter is also made out of waves, where the height of the waves is kind of like the probability that matter exists at that spot, and the frequency is the momentum. So just like volume and frequency are what's called a Fourier pair, meaning that a Fourier transform can turn one into the other, go from time into frequency space, you could do the same thing with matter using position and momentum. Position is a Fourier transform of momentum and vice versa.
Wow, that's amazing. That's mind-blowing right there. That just blows my mind.
And that's actually why the uncertainty principle exists. Because let's say you had a wave that existed at one point and nowhere else. We would know exactly where that was. But if we knew exactly where that was...
What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit 1 million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
Grand Canyon University, an affordable private Christian university, is one of the largest and fastest growing universities in the country, offering more than 270 programs online. In addition to federal grants and aid, GCU's online students received nearly $130 million in institutional scholarships in 2022. Find your purpose at Grand Canyon University. Private, Christian, affordable. Visit gcu.edu/myoffer to see the scholarships you may qualify for.
We wouldn't know how fast it was going. And the reason why is because you could imagine on this pond, if you tried to make a splash that was just 1 point, you would have to splash basically everywhere in the pond, if this infinitely large pond. And so you would not know anything about the momentum because you'd be splashing everywhere, where splashing is kind of like defining momentum. It's a difficult analogy, so you might need to listen to this twice, but it's essential for understanding virtual particles. And the reason why it's essential for understanding virtual particles is because the vacuum of free space does not have zero energy.
Yeah, that's amazing. Just the fact that what you just said there, that a vacuum does not have zero energy. And there's actually physical evidence of virtual particles in a vacuum. And it's something that I recently saw on a very old rerun of The Big Bang Theory, where they talk about the Casimir effect. This is a really trippy thing. Jonathan, do you want to hit on the Casimir effect?
Oh yeah, the Casimir effect is, let's say you have two plates that are very, very close together. The waves that are generated in free space of like matter and everything will either push apart or bring together these plates, kind of like magnetic energy.
And yeah, so basically you have these two plates in a vacuum, and there will be a positive pressure that either pushes them together. And again, isn't it dependent on the space between them? It's a fraction of the wavelength, isn't that right?
Yeah, it has to do with if it's a full wave or a half wave and destructive and constructive interference. But it is measurable, and there's actually a video on the Wikipedia article about it that shows how to do it with sound waves.
Yeah. So wow. So okay. And again, I believe that virtual particles in a vacuum average out to zero energy, but that's only the average.
Well, zero measurable energy, using zero useful energy, basically. And the reason why is because you could imagine the pond again, the pond of existence. Because there is an energy, there is a certain probability that a particle will exist everywhere. But the particle is not defined, so one of the particles can have negative energy. And what this means is that these particles, you could think of them as popping in and out of space, a pair of them, one going forward in time and one going backward in time, and just popping in and out of existence faster than you can measure it.
And the way we currently understand it, if I'm not mistaken, is it's always pairs. Is that right?
Oh yeah, I mean, yeah, because
it's never triplets. I mean, I know it's a dumb question, but I need to clarify for my own edification.
Oh yeah, no, they're definitely pairs, and the reason why they are pairs is because in the pond of existence, there is a construction operator and an annihilation operator. And what is an operator? An operator is just a type of wave.
It operates.
Yeah. So there's one wave that creates new particles and one wave that destroys old particles. And the way that this kind of works is like, let's say you send a photon. Let's say you go to a black light party, and there's black lights everywhere, and people are glowing because they're drawing on each other with highlighters.
That sounds like a lot of fun, actually.
Oh, it is fun.
Can we actually add some background techno to this section?
Absolutely.
Okay.
So when this happens, you have this photon that's almost ultraviolet that hits the highlighter. It hits one of the molecules in the highlighter, and it hits the electron, and in doing so, it beams out another photon. Now, what happens is that the old photon is destroyed using the destruction operator, but the construction operator creates a new photon. And this is, of course, done because when you beam it to the electron jumps up a shell, it gets farther away from the nucleus, and then but it's not stable there, so it goes back down, and in doing so, it generates a different energy photon, a different wavelength photon that you could see.
So I'm imagining, the way you're describing that, you want to know what's happening in my head right now? This episode is all about how black holes interact via gravitation with the universe around them. One of the topics we discuss is the absurdly strong gravitational field surrounding a black hole. To that end, our partner, Brilliant.org, has a course all about gravity called Gravitational Physics, which explores the ramifications of gravity. I love how the course takes you from classical Newtonian gravity all the way through gravitational fields, gravitational energy, the nature of orbits, and everything to do with gravitational physics. To support your education in math and physics, go to www.brilliant.org/breakingmath and sign up for free. The first 200 Breaking Math listeners can get 20% off the annual subscription, which we have been using. And now, back to the episode. At first, it was a pool table where, you had billiard balls disappear when they hit other billiard balls, but then a whole Rube Goldberg machine where parts of it disappear when other parts start happening.
And that's kind of what happens in the universe. The universe is not how we see it. It can only be understood through analogy, but it can be understood very well through analogy. And so what happens is that you have these construction operators, these destruction operators, everything is in harmony. And you can only measure a virtual particle is if you interfere with it using energy. For example, if you bring two plates very close together, you have the Casimir effect. Or if you destroy part of space using a black hole, you can also detect these particles.
Wow. So I think one of the main takeaways before we go into the next section is that virtual particles do come in pairs, and they pop into existence, and then they annihilate extremely quickly. And they have to have its pair to annihilate, like they crash back into each other.
And this is different than real particle annihilation really quickly because the terms are exactly the same, but they mean different things. When two real particles annihilate, they just change into two different types of particles. They do something that's conserved. Annihilation, in this sense, means complete destruction with nothing to show for it.
That's crazy. So that's almost like, as you said earlier, destructive interference in the wave. It's not anymore. It was, and now it's not. And that's just, it's weird. It's just weird.
Yeah, you could think of the universe as an accountant that is very, very picky about things. And you could think of a virtual particle as somebody returning something that they bought before anybody notices.
I like that. Yeah, some sneaky accounting there.
So why are we talking about virtual particles and black holes? How are they related?
Okay, so Stephen Hawking knew about virtual particles, of course, and he began to think about, well, how does this phenomena of virtual particles relate to black holes? As we said earlier, in the vacuum of space, virtual particles are always popping in and out of existence in pairs. So that means that even at the edge of a black hole, at the event horizon and near the event horizon, virtual particles are popping in and out of existence there too.
So now imagine that you have one of these virtual particles popping in and out of existence near the edge of a black hole. One of them falls in and the other one doesn't. Now, that means that when we're talking about the pond of existence, that the annihilation operator basically kind of fell into the black hole, but the construction operator did not, which means that the black hole gets smaller and as the particle goes away. And the reason why the black hole gets smaller is because, like we said, the universe is an accountant. What happens to the particle as it falls into the black hole is none of our business, because inside a black hole is not measurable.
Yeah, and that's a really interesting, I would say, crux of quantum mechanics is what's measurable and what's not measurable. And that's just something we kind of have to give up, wouldn't you say, in terms of understanding the universe is just what happens inside. We can't do that with modern physics, and it may not be possible at all. So then, when we're talking about virtual particles and black holes, Jonathan said when the annihilator operator.
Yeah, annihilation operator.
The annihilation operator goes into the black hole gets smaller. Something else that I want to say, when I was first reading about it, it highlighted the fact that outside of the black hole, you now have a real particle that exists in the universe that didn't exist before. And this is very, very important because, again, as Jonathan said, this is the universe being an accountant, as it were. So you don't have any more net mass or any more net energy. So although you have a real particle that's now radiating away from the event horizon, and that is actually called Hawking radiation, and it's a very, very low energy radiation, but it definitely exists.
Well, for normal black holes, it's very low, but the sum of all the energy over the black hole's lifetime is very great. It converts all of the energy into radiation. And when we're talking about the pond of existence, you might be wondering how black hole looks on that. So just imagine you have this infinitely large pond, and the thing is, there are splashes everywhere, but the splashes cancel out. That's 0-point energy, and those are virtual particles, the things canceling out. So now you can imagine you build an island, a round island in the pond. That's kind of like a black hole, because a black hole reflects the operators. The annihilation and the construction operators are essentially reflected. And I say essentially because they have to be redesigned around a black hole. But the annihilation operator, the new annihilation operator, is a combination of the old annihilation and construction operators, and so is the new construction operator. And the crux of this is that because the splashes that would be happening on the island are not happening, and because the splashes that are happening outside of it are reflected, that essentially creates radiation. It's the same thing, that's the macroscopic view versus the microscopic view.
Yeah. And as we said earlier, with that annihilation operator, the black hole very, very slowly gets whittled down, and after a very, very long time, in fact, evaporates. Now, that is not an insignificant event. As we said earlier, this has huge consequences. As we had mentioned, we know that whatever goes into a black hole will never go out. So what about when a black hole evaporates? Is information destroyed? And I'd like to say, so if you were to add up all of the Hawking radiation that comes off of a black hole from the virtual particles, if you were to add that up, would that add up to less than the sum of all the mass of other things that went into the black hole?
The mass, well, the energy is the same. When it's a large black hole, it evaporates mostly photons. Very small black holes evaporate things like electrons and other things. They're extremely high energy, as we'll talk about in a bit. But energy is conserved with the black hole. And remember, mass is energy, E equals mc squared.
So in other words, like, let's say that you did have a black hole of any arbitrary size, and throughout its lifetime, it sucked in a bunch of things, a nebula, some planets, all kinds of things. The effect of virtual particles over the life of the black hole will eventually cause it to evaporate. What I'm saying is, will any information, according to Stephen Hawking, any information about what went into it, when that black hole evaporates, it's gone. Is that right?
Essentially, but I think an analogy will clear up why there's confusion around this, because the black hole evaporating actually solves the violation of the second law of thermodynamics. Otherwise, black holes would reduce entropy, because if you threw a very hot thing of gas into the black hole, like we said in the previous episode, the universe would get a little bit less entropy, and that is impossible because any closed system can't reduce its entropy. So the analogy I'm thinking of is, imagine a couple of kids in an overcoat trying to get into the movies. So they get into the movies, and then they get out of the overcoat, and then they're walking around, they get popcorn, whatever, and then one of them goes to the bathroom and changes their shirt because they wanted a new shirt. You can't see them going into the bathroom, and then say they go through an air duct or something, we don't know what happens, and they come out of a different bathroom. Everything is conserved, but we weren't able to follow them. If we had cameras, we would have a gap, and that's what is really disturbing to a lot of people, is that there doesn't seem to be a direct line of accounting. However, there's been research, which we'll talk about in the next episode, which says what might happen to the information and how the information is actually conserved on the surface of the black hole. Because as we said, one bit of information increases the surface of a black hole, no matter what size it is, by the same amount.
Now, when this first came out, there were a lot of physicists who were very bothered by this, including Leonard Susskind, as well as a gentleman who I'm having a very hard time pronouncing. I feel bad about this. Gerald T. apostrophe Hooft.
Yeah, I don't know.
Gerald
I don't know.
I'm sorry. We can edit that out or not. I'm sorry. I'm not doing
Dutch
great.
names are hard to pronounce.
Yes, they are. He's a very, very brilliant physicist, but they were very, very bothered by it. Actually, watching the Hawking Paradox documentary on the BBC, Leonard Susskind recounts after he was first introduced to the idea of the information paradox, he was so shaken by it that on his drive home, he said that it was raining and there was a lot of fog on his windshield. At every single stop, he would sit and with his finger do physics equations on the window because he just didn't want to believe it. It was just that disturbing for him. So maybe we can talk about a few reasons why somebody like Leonard Susskind might find the idea very disturbing.
Yeah, like for example, like if Hawking radiation didn't exist, it would violate the second law of thermodynamics, and information destruction itself does violate the second law of thermodynamics. So even if that violation is like instantaneous or temporary, it is an apparent violation. Maybe it's a virtual violation.
There are other scary consequences of the idea of information being destroyed. This essentially means that causality doesn't exist, which would mean that the way we know things about the universe would essentially not work.
Because remember, causality and the conservation of information means that everything has a unique previous state. So let's imagine you have a book and you throw it into a black hole and it's destroyed. If a black hole can destroy information, that means you could have thrown anything into that, which means there's a whole bunch of different past circumstances which could exist. You destroy causality because you create basically a web of causality, which isn't the way that we currently understand causality in quantum field theory.
Yeah, and for physicists who are really, far deep into this area, there's other consequences as well. For instance, there's no reason why virtual black holes couldn't exist in your own mind that would destroy your own memories. You couldn't even trust your own memories. This is the idea of information being destroyed is a very, very big deal.
Yeah, because it means that if causality doesn't exist, then everything that Francis Bacon said about science is wrong, essentially.
So, the destruction of information is not good. It's no bueno. However, we know that in the universe, we don't have the destruction of information, even with all the mysteries surrounding black holes. We know this because
the universe is not boiling hot. The universe would be extremely hot if black holes destroyed information. Because at the beginning of the universe, it created a lot of very small black holes. And some of them still exist. And yes, black holes are at the center of galaxies. They're part of our universe. So they would heat it up very quickly because of the destruction of information.
Yeah. While researching this episode, actually, we did some calculations of some black holes. Jonathan, what's the temperature of a Schwarzschild black hole that is 1 kilogram?
And just real quick, a Schwarzschild black hole is a black hole that is not rotating and that has no charge. Because remember, a black hole from last episode it has like 3 properties. It has mass, it has charge, and it has rotational energy.
Yeah. So again, Jonathan did some calculations, including the temperature of a 1 kilogram black hole.
And the temperature is 1.22 times 10 to the 26th. That's 122 with 24 zeros after it, degrees Kelvin.
And that's just from all the crazy virtual particles popping out, right?
Yeah, and just to give you an idea of how hot that is, because it's so high, because Kelvin is just 273.15 degrees more than Celsius at any point, so you can't have negative degrees Kelvin. But 1.22 times 10 to the 26 degrees Celsius is very hot. It's
really hot.
So many. It's almost incomprehensible. There's nothing we could talk about that would make sense. It's just so hot. Yeah, I think it's hotter than than an atomic bomb. Actually, even it's hotter than the center of the sun. It's very hot, and this black hole over its lifetime will turn all of its mass into radiation, and that radiation over its lifetime is equal to 21,000 kilotons of TNT.
Wow, that's a lot. That is an excellent power source.
Yeah, it's a little dangerous. Anything that it touches gets sucked in and destroyed forever. Or
Still,
does it get destroyed?
Fantastic source of sci-fi, and I'm sure I have not read all the sci-fi that utilizes black holes.
Now, how do we get to 1.22 times 10 to the 26 degrees Kelvin? That's the temperature of a black hole formula that was discovered by Hawking and friends. Now, we're going to talk about the formula, and it's pretty mathy, but it involves so many constants that are used in other formulas and are used in physics that it's kind of mind-boggling. It kind of combines them all.
Yeah, I don't keep a lot of math details in my head, but for the sake of this formula that we're going to talk about, if you can at least pay attention to each of the constants that we talk about, and you can process it later. that's kind of the way that was my take on it. At least it's certainly helpful.
Yeah, so it's equal to the reduced Planck constant divided by all of the following. The speed of light times 8 pi g over c to the fourth. That's 8 pi times the gravitational constant divided by the speed of light to the fourth power. And we'll show why we're using that twice, the speed of light twice, because some of you might be wondering, why didn't I put the speed of light cubed on top? Times the Boltzmann constant times the mass of the black hole.
Jesus, it's like a 8 triple quadruple decker sandwich made out of all the physics constants all together.
Oh yeah, it's amazing. And we're going to go through each one of these. So first, the reduced Planck constant. To talk about that, we're going to talk about the Planck constant real quick. Yeah. Let's say you have a photon with a certain frequency. The energy of that photon is equal to the Planck constant times the frequency, but it's used in so many other things too. One of which being the uncertainty principle, the modern Heisenberg uncertainty principle, which says that the standard deviation, meaning how fuzzy basically the momentum is times how fuzzy the position is greater than or equal to the Planck constant divided by 4 pi. And the reduced Planck constant is just the Planck constant divided by 2 pi, and is sometimes called h bar. So that's the first constant, and everything else it divides by.
Oh goodness, man! I'm out of breath. I feel like I'm in like a really hard spin class, and I'm just it's my first day, and that was the first rep. You know what I mean? So stay with us. Stay with us.
But we're gonna up the resistance. Maybe we'll put some more techno music.
Throw
like
the techno on there and get through this equation. Woo! Feels good. Okay.
So next constant is 8 pi g divided by c to the 4th, and that is related to how matter and the curvature of space-time relate to one another. Because if you remember, the fact of gravity exists because of the curvature of space-time. So space tells matter where to go, and matter tells space how to curve. So it's the Einstein tensor, which is a whole thing. You could actually check it out on our tensor poster, is equal to 8 pi g over c to the 4th times the stress energy, which in the stress energy is things like the energy of the particle itself, like E equals mc squared, the momentum, the shear stress, and the pressure. All of those create gravity waves. And that is the constant that relates to those.
Oh man, so again, if we're using the analogy of the spin class at a gym, I feel like I'm just out. My legs are still pumping, but I'm just kind of in a zombie mode.
And remember, real quick about that too, G is the gravitational constant, and that is the force that is between two massive objects. So you take the mass of the two objects, multiply them together, divide by the square of the distance between them, and then you have your proportionality constant, which is G, and it's very, very small, because gravity is incredibly weak. To prove that to yourself, rub a balloon on your head, and then put it on something else that sticks to it. That is doing more than the pull of the entire Earth on that balloon.
And then after that, we got some that are, okay, this is the downhill part of the spin class.
We're going to reduce the spin.
The resistance. Yeah, so now we're now if you shift into low gear here, the next part of the equation we'll talk about is C, which is just the speed of light. Whee!
And speed of light is how fast information can go. Nothing can exceed the speed of light, because if it did, it just doesn't. Like if you look at the formulas for even special relativity, going faster than the speed of light just doesn't make sense as a thing. It's like saying, I want bread that's extra bready.
Sorry, man. Far out, man. Far out. All right. So, what do we have up next? Boltzmann's constant, which is K with a subscript of B. Is that right?
Yeah, and Boltzmann's constant shows how much energy a particle has in a gas. So let's say you have a balloon with a certain temperature. You multiply that temperature by the Boltzmann constant, and you get the energy of one particle in that gas, an ideal gas. And it doesn't matter what the gas is, it'll have the same thing. And so that's an energy of each particle given the temperature of many. And that's different than E equals hf, which is the Planck constant, which is the energy of one particle given the frequency of 1. So we have microscopic laws, macroscopic laws, and all of these are multiplied together on the bottom. And
awesome. Oh, I'm sorry. Did I interrupt you?
No.
Flow? Okay, I was going to say, we are now down to home stretch. We've got one more element in this equation, and that is the capital M.
Which is just the mass of the black hole, how much it weighs. And you might say, how can we put a black hole on a scale? It'll just suck in the scale. We can measure the mass of an object in space just by seeing how it pulls on other things, because remember, gravity exists, and black holes do not violate gravity. If we made the Earth the size of a cranberry, it would change into a black hole. And the moon would just keep orbiting, and the black hole would keep orbiting the sun until it evaporated, and it'd be fine, basically.
Yeah, so you don't measure it directly. Kind of like, yeah, exactly. Sometimes you don't want to measure how heavy something is, but you can infer.
Yeah, and the weird thing about this is because the mass is on the bottom, that means that bigger black holes are colder. So the bigger a black hole is, the colder it is.
So finally, when you put all these constants together, we've got S, which is the entropy of the black hole, equals K, subscript B, times the area of the black hole, times the speed of light cubed, all divided by 4 times the gravitational constant times h bar. Whew, that's all of it.
And that means that the entropy of a black hole is dependent only on the area of a black hole, which means that the boundary of a black hole, the area that is the black hole, is the only thing that creates entropy. And that means that entropy must be stored there. So the information paradox really at this point is, does the Hawking radiation conserve the information, or does it create new information? Or what happens there? Is causality violated? What happens to the network of causality? We have to answer these all in the next episode, probably.
That's right, and that is the equation that I'd get a tattoo of if I were to ever get a physics tattoo.
How many emails would it take for you to get that tattoo?
Do I have to commit to this?
So Gabe has always talked about the information paradox formula and how he might want to get it as a tattoo.
And I've been so on the fence about it, but here we go on the record. If we get 100 emails in a period of 2 months, then I will get this tattoo.
Yeah. So just email us with anything, questions, whatever, and we're not going to count the emails we do for business. And if we get 100 of them, Gabe will get a tattoo, and we'll post the video of him getting the tattoo on the Facebook page.
That's right. You heard it here first.
Information seems to be destroyed when it goes into a black hole, but we observe a universe in which that does not occur. However, we do not technically know if the information that goes into a black hole is the same that comes out, because we lose the train of accounting as soon as we involve the event horizon. And studying black holes involves much of the physics that we have discovered in the last century and a half. So what can we do with such interesting objects? And what is the current state and the future of the study of black holes? Stay tuned for the next episode. I'm Jonathan.
And I'm Gabriel.
And this has been Breaking Math. Gabriel, do we have anything to plug?
Yes, we've got a substantial amount of things to plug. I made a list. I have a list of reading that I've done. The first thing I want to plug is not related to black holes. The first thing that I want to plug is a work of fan fiction that I've read that is so fantastic that I just wanted to share it with all the Breaking Math listeners. I read a book called Harry Potter and the Methods of Rationality. It's written by I'm not prepared here. It's written. I will get you the author's name. Essentially, a devoted fan of Harry Potter rewrote the story, not the entire story, but, parts of it, as though his parents are not the Dursleys, but professors at a college. I think maybe chemistry and mathematics or something like that. I don't quite recall. But every chapter has Harry intensely analyzing phenomena around him, in the magical world of Harry Potter, and he looks at it from all angles, and he uses the Francis Bacon method, the Francis Bacon scientific method, where you test for positives and for negatives. And he talks about the mathematics of Richard Feynman and the book Gödel, Escher, Bach. In fact, the chapter I just read was a chapter where he has the sorting hat on, and he is thinking about the consciousness and the awareness of the hat. And the hat reads his mind thinking about the hat's own consciousness, and it becomes a strange loop, and the hat becomes conscious all of a sudden. It references Gödel, Escher, Bach.
Which we did an episode on.
Yeah, we did. So if you guys are looking for something really great to read, I would Google search Harry Potter and the Methods of Rationality. It's so enjoyable.
We also have the poster to plug. The prints have been ordered, and they're shipping soon. So if you want to get a poster, they're $35 on our Patreon. The price will go down at some point, but right now that's basically breaking even for us. We just want the poster to be, we don't want you to have this poster. We worked hard on it.
Yes. It's been a very, very long process to get the prints correct. Earlier this past year, we had prints from so many shops, and they were never of a quality that we were happy with. They always had strange lines on them, or the paper was too thin. We finally found the shop that has the equipment to get us what we need. So those posters are being printed, and they are being shipped very, very soon. So yeah, make sure you check out the Patreon. What's the Patreon website?
Patreon.com/BreakingMathPodcast. We're also on Facebook at Facebook.com/BreakingMathPodcast. Twitter at BreakingMathPod. We have a website, BreakingMathPodcast.com, which will be updated soon, and it really needs to be updated. And one thing I also want to plug is PBS Space Time. it helped a lot with this episode, at least, getting some of the stuff primed. And it goes into a lot of detail. It's if you like another plug, 3 Blue, 1 Brown, it's very much like that.
Yeah. Was there a specific episode of Space Time, or did you just kind of flip around on it?
Oh, I lost count of how many episodes I've watched.
Okay, yeah. And of course, as you guys know, we've mentioned so many times, I think that the book, The Black Hole War by Leonard Susskind, is absolutely required reading. I did say that parts of it are, how do I explain this? There's so much brilliance in it that it's a must-read. But I'll also say that there's other segments where he's not talking about black holes, and instead he's talking about,
sandwiches and stuff.
Yeah. Sandwiches or shopping or something.
But it is charming. You get to love him throughout the book.
You get to love him. Yeah. So I would say it's a must read for sure. That as well as the BBC documentary on the information paradox as well. All good stuff. And I think lastly, there's a podcast that we really, really admire.
Very good friend of the show.
Yes, a very good friend of the show. There's a podcast that we want to talk about called the Mad Scientist Podcast. Now, this is neat. It's a slightly different style than Breaking Math. They talk about science, skepticism, and culture, which means that a lot of the episodes are about the occult. They've got episodes that are about medical marijuana and the science behind it. They've got a recent series, a 4-part series, all about UFOs. Now, let me tell you about one of the founders, Chris Cogswell. He actually has his PhD in chemical engineering.
We actually had an episode, it was a joint episode from all the podcasts called, if you look it up, it's BFNB 1 and BFNB 2. The first one is Food for Thought, and the second one is Thought for Food.
Yeah. And the that acronym stands for blank for non-blank. It's part of...
which is now called Ciencia Podcast, which is a podcast collective that we're associated with.
Yeah. There was a lot of plugs there. I realized that. That's quite all right. There's a lot of plugs in this episode.
In a world where black holes run rampant, a hero is needed, and one comes just in time. Somewhere, an adventure in space and time.
Oh no, I've divided by 0.
You divided by what? It's become sentient.
I know you're virtual, but I have a gun!
Black Hole Heist, coming to a theater somewhere, probably.